In this video, we're going to continue with our sets intro, but just doing some extra examples to get some practice with these things. So in the first example, U is the set containing the numbers 1 to 9. A is the set of all even numbers within the universe, so 2, 4, 6, and 8. B is the set of all prime numbers in that set, so 2, 3, 5, and 7. And C is the set containing the numbers 1, 3, 6, and 9. So the first thing it asks us to do is compute a complement. So remember, these are all the elements in U that are not in A. So A has all the even numbers, so the leftover ones are going to be all the odd numbers. So this set is going to contain the numbers 1, 3, 5, 7, and 9. Next, we want to compute A union B. So remember how we did that before. We wrote all the elements of one of them, it doesn't matter which one, so I'm going to do A first, so 2, 4, 6, and 8. And then I want to look to B and see what did I miss. So we already got the 2, but we're missing the 3, the 5, and the 7. So because the union contains everything that's in at least one of A or B, any element we see in A or B will all be in the union. Now we want the complement of this union. So we just computed it. Now notice that the numbers are not in increasing order, the way I've written them. That doesn't matter, because the order we write them doesn't make a difference. If you want to write them in increasing order, you're welcome to. It might be easier when we're trying to compute the complement, but if we just think about this, it looks like we're missing the numbers 1, and then we have 2, 3, 4, 5, 6, 7, and 8. So we're just missing 1 and 9 here. So the complement of that set is just the numbers 1 and 9. Now for D, we're doing A intersection bracket B complement union C bracket. Okay, so these brackets are important. Remember, you have to do the bracketed bit first. So in order to do that, we might want to have B complement ready. Okay, so B complement is all the numbers that are not 2, 3, 5, and 7. So we're going to have 1, 4, 6, 8, and 9 in that set. And now when I union this with C, I'll just write down all the numbers in B complement. And then see, does C have anything extra? Well, it has the 3 is extra. Okay, so now I have this set to work with. So now I want to intersect it with set A. So A has all the even numbers, so I'm just going to look for even numbers here. And I see that 4, 6, and 8 are all there, but we're missing 2. So this intersection is going to contain the numbers 4, 6, and 8. Okay, part E looks very similar. Okay, the symbols are the same. So the intersections are first, the unions are second. All we did was move the brackets. Okay, now it's not clear at this point whether or not that's going to matter. Okay, so remember, we have to do the brackets first. So let's compute A intersect B complement. So we're looking at B complement again, and we want to know what does it have in common with A, which are the even numbers. So here again, I'm going to have 4, 6, and 8. Okay, now I want to union this set with C. So, oops, I usually use purple for my answers. So I'm going to start by writing what's in this set. So 4, 6, and 8. Okay, so these are the elements in A intersect B complement. And now I want to say, does C have anything extra? Well, it definitely does. It has a 1 and a 3 and a 9 extra. So the only thing we already had was the 6. So notice that they are different. So the order that you do these things really matters. So they should always have brackets present so you know which order to do them. Okay, next example, we have a bit of a weird universe here. So we have the letters A, B, C, D, and E, and the colors blue, red, and yellow. Set A only has the letters A, B, C, and E. Set B has the letter B in the color blue. And set C is using set builder notation. So you read this as X, so X is X in U, so an element of U, such that X is a color. So what that means is that set C is actually just going to contain all the colors, because those are the only elements of U that represent a color. Okay, so we want to start by computing B intersection C. So what do B and C have in common? Well, just the color blue. Okay, so that one wasn't so bad. Now the next one, I want A complement union C. So again, it's nice to write out all the sets you're working with. So what's the complement of A is going to be everything that's in U that's not in A, so D, and then all the colors. Okay, so then when I union that with C, I can start writing out these colors, and the D, sorry, so everything in A complement. Okay, so these are all in A complement. And now I want to say, okay, is there anything extra in C? Well, there's not, actually. We already got all the colors, so nothing extra. So C is actually a subset of A complement. Maybe I'll just write that here. C is a subset of A complement. So the union is actually just equal to A complement, the sort of bigger one. Okay, next we want A intersect B intersect C. Now notice there's no brackets here. That's not a problem because these symbols are both intersection. So I want to know, what do A, B, and C have in common? If it's hard to see that, you can take any two of them and intersect them. So I'm going to do A and B. And I'm just going to get the letter B. And then I want to intersect that with C, which C doesn't have the letter B. So this has no elements. Oops, so it's actually the empty set. Okay, so there's no elements in that. The A, B, and C don't have anything in common. Okay, now I want the complement of A union B intersects C. So we don't have A union B yet, so let's write that. Okay, so it has everything in A, and then everything extra in B, which is just the color blue. So then the complement of this is going to be, so what's missing? D, the letter D, and the colors red and yellow. Okay, so now I want to intersect that with C. So what does this set have in common with C? And well, that's just going to be the colors. So we're going to have the set containing the colors red and yellow. Okay, lastly, we want A intersect B complement, union B complement intersects C. So again, we're going to want to do some computations here. So what is A intersect B complement? We don't have B complement yet. So maybe we want to write that. So B only has B in blue, so the complement is going to have A, C, and E, and red and yellow. Okay, so when I intersect that with A, I'm just going to have A, C, and E, so no colors. Okay, now if I do B complement intersect C, so what does that have in common with C? Well, that's just going to be the colors, so red and yellow. I lied to you a bit here. This B complement should also have a D, but that doesn't affect our other computations because neither A nor C have the D. So now I want to union these two sets together. So I can just write out the elements in the first one, so A, C, and E, and then add the extra elements in the second one. They actually had nothing in common. Okay, so this is A intersect B complement, and this one is B complement intersects C. So when we union them, we get all of those. Okay, so in our next example, we don't have our sets explicitly listed. So the universal set is a set of all Camosun students, and we have subsets. A is all Camosun international students, and B is Camosun students above the age of 25. So we want to know who would be in the set A complement. So this is within the universe, so it has to be a set containing Camosun students. Camosun students, and we don't want them to be in A, so that means that they're not international. So Camosun students who are not international. Okay, another word for that is domestic. So they're domestic students. A union B would mean that they have to be in A or in B or both. Okay, so they have to be Camosun students in order to be in the universe. So they're Camosun students who are international, because that would put them in set A, or they're above the age of 25, okay, or both, possibly. Okay, now the last one, A intersect B complement. So there have to be in A because it's an intersection. So it's the set of Camosun international students because they're in A. Now they're not in B complement. So that means they're not above the age of 25. So this means that they are 25 years old or younger. Okay, let's try another one. So here I have set A is the letters in the word calm, and the universal set is the letters in the word musical. So notice that the letters in the word calm are in the word musical. So we want to list all subsets of A that have exactly 2 elements. Okay, so remember how we do a subset? We want only letters from A. And so here they have to have 2 elements because we want exactly 2 elements. So I could take C with A, that would be a subset, or I could take C with L, that would be a subset, or I could take C with M, that would also be a subset. Now I've paired C with everything, so now I can't take C. Maybe I take the A, and I could put it with the L, or I could put it with the M, and now A is all used up. Now lastly, I could put the L and the M together. So I have 6 different 2-element subsets of A. Now, part B and part C actually ask for an example. Okay, so there's many different answers here. Okay, so these two have many correct answers. Okay, so if you put one and it doesn't happen to be one of the ones I put, that doesn't mean it's wrong. So give a 2-element subset of U that is disjoint from A. Okay, so again, I want a set with only 2 elements, but I want it to be disjoint from A. So we have to remember what it means to be disjoint. So this means that it has nothing in common with A. So that means when we're making our subset, we just don't want to use any elements, any letters that are in A. So an example would be U and I, for instance. So that's a 2-element subset of U that doesn't use any elements from A. Okay, we could also use the S and the I, for instance. Okay, so those are just 2 examples. As long as you pick letters that are not C, A, L, and M, and there are 2 of them, they're from U, you're going to get a correct answer here. For part C, we want a subset of U that is not disjoint from A, so that means it has something in common. okay? But it's also not a subset of A. So what that means is that it has something not in A as well. Okay, so again, there's going to be lots of different answers here, but we could take something with a U and maybe an M. Okay, so it has two elements. It's a two-element subset, but it's not disjoint from A because it has the M in common, but it's not a subset of A because it has a U, and U is not an A. Okay, or we could take a bigger one, so maybe we have M, U, and I. Okay, so it has the M that's in common, and it has U and I, which are not in A, so then it makes it not a subset. There's lots and lots of different examples here that are correct. Okay, lastly, so let's say I have a universal set U and subsets A and B. We want a condition that would ensure, for first of all, A intersection B is equal to the empty set. Now this condition is kind of the definition. I just put it in here sort of to remind you. So when A and B, the intersection is empty, this means that A and B are disjoint sets. Okay, so that's sort of a condition. Now these next ones are a bit different. So when would it be that the intersection A intersect B is just equal to A, is actually equal to A? So what that means, okay, is that everything in A is in A intersect B, right? Because these two sets are equal, so every element that's on the right side has to also be present on the left side. And in order to be in the intersection, it has to be in both sets. So that means everything in A is also in B. And that's the definition for A being a subset of B. So that's the condition we need here. If A is a subset of B, then A intersect B is actually equal to A. Okay, we can use similar reasoning in part C. So here the union is equal to A. So that means, so if I think about, let's start with the left side here. So A union B contains only elements from A. Right? So there's nothing extra because the two sides are equal. So everything on the right side has to also be on the left side and vice versa. So what that means is that when we computed A union B, B added nothing new. So remember how we do the union, we start with one of them, write all of its elements, and then we look at the other one and say, is there anything new? So if we did A first, it means that B added nothing new, which means that all elements of B were actually elements of A. So what that means is that here, the condition that we need is B is a subset of A this time. And those are just a few examples regarding sets.